There we go. All right, cool. We got that going. All right, so this is a continuation of what we talked about on Monday. So when we talked about on Monday, at first, we talked about how Aleph null is actually defined. It is the cardinality of the set of natural numbers. That's how it is defined. And then we looked into integers, and we found a function that can map integers onto natural numbers. And that function turns out to be bijective. So now we can claim that the cardinality of the set of all integers is the same as the cardinality of the set of natural numbers. So they are both basically Aleph null. So that's the important part of Aleph null is any set that has a cardinality of Aleph null is known as infinitely countable. Okay. So now we looked into the two-dimensional problem, and we ask, if I give you a pixel system, okay, so we have x-axis and y-axis, and we only use natural numbers as coordinates. So the question is that system also going to have a cardinality of Aleph null? Okay, so let me kind of show you. So I never really explained, what is the domain and what is the codomain of G, the function that we have started to talk about on Monday. So we can start with that. So the cardinality, or not cardinality, but G is kind of like this. So G is a function. It maps the Cartesian product of natural numbers to natural numbers. Or, that's the intention. So is that notation understood? Hmm? It's an N. Oh, it's because of the grid that's interfering. I can get rid of the grid. Go to page, change paper style to plain. There we go. Better? Okay. It's better than a piece of paper because I can change the background. So that's what G is, okay? As a function, it is supposed to map the Cartesian product of natural number to just natural number. So the question is, well, can it be done? Well, we found a way to do it. Okay, so, I'll give you an example here. So if this is 0, 1, 2, 3, 4, we are talking about the x-axis here. And we are talking about now the y-axis, 0, 1, 2, 3, 4, 5, and so on. So the way we fill this up is we put a 0 here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on, okay? So this is how we filled it up. Basically we're just drawing diagonal lines. So we start with the corner, and then we have one really short diagonal line, one that is longer, 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 and even longer. So when you look at the number of pixels on each diagonal line, the one to its left has one fewer item. Okay, so if you count the number of pixels on a particular diagonal line, it goes from 1, 2, 3, 4, 5, and so on. So that means when you look at everything that has a y coordinate of 0, it is 0. Then we have 1. Then we have 0 plus 1 plus 2, 0 plus 1 plus 2 plus 3, and so on. So on Monday, we talked about how we can get a closed form of that particular value. In other words, on Monday we looked at okay, let's focus on g of a particular pixel, but all of these pixels have a y coordinate of 0. So we're only changing x. So as it turns out, g of x0 is basically just the summation of 0 up to and including x. Okay? And then we use the sigma notation. the sigma notation is not known as a closed form, which means you kind of have to expand it and add everything up to get the value. So we ask, well, can we get to the closed form? So through all these derivations, which mostly have to do with tricks with, within the summation of a series, we come to the conclusion that, if you just add 0 all the way up to x, the end result is, oh, it's really easy. It's really just x times x plus 1, the whole thing divided by 2. We're done. Is that okay? So now we want to ask the question of, well, what about all of the other pixels? Okay, so now let's take a look at this picture here. So instead of looking at the values of each pixel, this time we look at the coordinate of each pixel. So we got 0, 0, we got 1, 0, 2, 0, 3, 0, 4, 0, and so on. On the other side, we have 0, 1, 0, 2, 0, 3, 0, 4, and so on. And in between, 0, 0 is one diagonal line by itself. It only has one pixel. 1, 0 and 0, 1 is another diagonal line. 2, 0 is the first or the base of the third diagonal line, but it has another pixel in between with the coordinate of 1, 1, and then 0, 2. And then 3, 0 has the next pixel here being 2, 1, and then we have 1, 2, and then we have 0, 3, and so on. So are we doing okay so far with these two pictures? The one to the left is really showing you the natural number mapped to a particular pixel, and then the one to the right is really just showing you the coordinate of each pixel. So pretty boring stuff, okay? But what we need to do is to say, well, if I give you a random pixel, okay, at a particular place, okay, I'll call it xy. So if I say, okay, I have a pixel at coordinate x and coordinate y, coordinate x, y, what is the natural number corresponding to that particular pixel? I want to be able to answer that question. Is that okay? Huh? It's not quite that, okay? So it's a little bit more than that. So the first thing we need to do is to find out which diagonal line does it belong to. Now, why do we want to do that? Because if you can find out which diagonal line it belongs to, what do you think is the pattern of pixels on the same diagonal line? It's just a sequence, right? So if you look at this particular diagonal line, it's 10, the natural numbers are 10, 11, 12, 13, and 14. So the y coordinate is what you add to the natural number at the base to get to a particular value on the diagonal line. Is that okay? So we want to know which diagonal line it belongs to. But how do we find that? So we have to now try to recognize what is one particular pattern that we see across the coordinates of every pixel of the same diagonal line. Well, do we find anything that is regular? Is there a pattern? 3, 0, 2, 1, 1, 2, 0, 3. Those are the pixels of the same diagonal line. What do you notice? At exactly the same pace, which means the sum of the xy coordinate stays constant on the same diagonal line. Aha, okay, but that's kind of cool, because if I add xy here, that will tell me where the base of that diagonal line is. Is that okay? So x plus y always tells me where the base of the diagonal line is. How do we compute the value at the base of the diagonal line? We got that x plus 1, the whole thing divided by 2, right? So now we can extend that particular reasoning, and then we can say the base of the diagonal line of xy is at x plus y 0. Is that okay? because every pixel on that diagonal line must have the x and the y coordinates to add up to the same sum. So, well, if this x plus y, adds up to a particular sum, then at the base of that diagonal line, we still need the x and the y coordinates to add up to the same sum. But since we know at the base, the y coordinate is going to be a 0, so that forces the x to be x plus y. Is that okay? So what is the g value of that thing then? So the g value of this particular pixel, according to what we have already worked out, is x plus y times x plus y plus 1, the whole thing, divided by 2. Right? So, but that's only at the base. This particular coordinate is not at the base. But how far is it off from the base? Y, right? The letter Y, not WHY. Okay, so that means if I just add Y to this whole thing, then we get the G value of XY. Is that okay? Well, are you guys just going to say, yeah, we buy that? Well, we have to try it out at least a few times, don't you think? Okay, so we'll try out something that we should know already. Let's try 2, 3, okay? So we'll try to figure out what is the natural number corresponding to the coordinate of 2, 3. So according to this, it is 5 times 6, the whole thing divided by 2 plus 3. So that's 15 plus 3, which is 18. Okay? Well, is it really 18? Well, let's go back and extend our picture here a little bit. 15, 16, 17, and we got 18 here. Well, is that 18 really corresponding to the coordinate of 2, 3? X is 2, y is 3. So it does work. Is that okay? Kind of cool. Well, the next question is, before we can claim that the cardinality of the Cartesian product of natural number and natural number is also the same as the cardinality of just natural number, before we can make that conclusion, we kind of have to make sure that this function g is bijective. Bijective means it is both injective and surjective. So you have to ask the question, if I give you 2 different pixels, okay, do they map to different values? Do we reuse numbers? We do not reuse numbers. The natural numbers, because every single time we assign a number to a particular pixel, we increment the counter automatically, which means, in a very loose argument, we can now argue and say that, we do not repeat the same number on 2 different pixels. Okay, I know it's not very formal, not very, it's not a formal proof, but in terms of the concept, it seems to make sense because we have a counter, it keeps incrementing as we move across the pixels. Okay, so it's injective. Second question, is it surjective? Well, surjective means are everything in the codomain used, mapped to. So you can say, okay, I bet you that this particular natural number is not mapped to. Okay, let's say you want to use that as a counter argument. Okay, how do I say that? No, that cannot be true.
It's defined in terms of the diagonal starting from 0, increasing, so it has to cover every single one. Like,
yep.
How do we decide it does?
Yep. Eventually, we'll get to that value. So that's also a kind of loose argument, in terms of why it is surjective. But I think it kind of makes sense intuitively that it is surjective. Oh, it is both injective and surjective. It is bijective. So the first thing we can now say is the cardinality of n Cartesian product with n is actually out of null. Okay, nobody seems to be puzzled or amazed. Really? Okay. It's really kind of profound in a way because we are collapsing a two-dimensional space into one dimension. And it has the same cardinality. Okay, nobody seemed to be amazed by this. You know, when I work on this note here, I go like, that is pretty cool. But what makes it even more cool is what if you start with a five-dimensional space? So you have n Cartesian product with n, Cartesian product with n, Cartesian product with n, Cartesian product with n. What can you do about that? Does that have the same cardinality as just natural number? Let me show you what I mean, you know, by writing it out. So the question is, okay, I'm just going to use n here because, you know, the funny n takes a little bit longer to write. So we have n, 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 n. Does this particular set have the same cardinality as just n itself? It does, because what we can do is we can use G to map these two into one n first. Okay, so we apply G and collapse that into one single n. And then what do? We take these two n and go through G and map it to another n. We take this n and this n, use a G to map it to yet another n, and then we finally take this last n and this second last n, go through G and map it to another n. So yes, a five-dimensional space really collapses to a single dimension. Yeah, you first and then you. Yep, go ahead.
N to the power of k
Yeah.
is all null.
Yes, as long as k is constant, right?
Right.
Yep. As long as k is finite and constant, yes, it collapses to just n. Yep.
So if it's not finite, then it doesn't work, right?
Well, if k is not finite, you know, you're basically looking at a limit issue, right? So it doesn't quite apply, you know. So k has to be a constant, it has to be a finite number. But it is still interesting because what it means is if you have a three-dimensional, you know, thing that you want to express. Now we got all kinds of stuff that we need to express in three-dimensional space. If you go to the design hub, okay, we got 3D printers, right? So with a 3D printer, we need to know, okay, where is that plastic, you know, supposed to go, okay? Okay, that's three-dimensional. You look at the screen, it is actually, the screen itself is two-dimensional, but each pixel of the screen is three-dimensional because you got RGB dimensions. Is that right? Okay. So that means we have a total of 5 dimensions. If you look at both the spatial thing and all the potential colors that can be on a particular pixel, it is a 5-dimensional thing. And yet, we can encode all of that stuff into a single dimension as natural numbers. Yep.
If you wanted to go to like Z by Z, would you use this mapping along with the mapping we did earlier?
Yes. So we would combine the f that we used earlier, you know, that maps z to n. Then we fold n and n into n, and so on. Yes. So we can stack those functions. Because all those functions are bijective, so as you stack those functions, the stacked version is still bijective. All right? Okay, you guys don't seem to be impressed at all. Tough crowd, exactly. Tough crowd. All right. Well, but here's another question. If it is bijective, it means there's an inverse function. Because that's also what we talked about when we talked about, you know, if a function is bijective, that means, you know, it has to have an inverse function. So now we want to look at the inverse function and say, if you just give me a natural number, not in this, you know, kind of complex case, but in the case of, you know, n cross n to n, okay? If this is g, so that means I have an inverse function g to the power of -1 that will map a natural number back to a coordinate in 2D space. I mean, that's, because we are just reversing the domain and the codomain. So now the question is, well, how do we figure this one out? What do you think? Well, it's all math, right? And of course, some people will be asking, so why are we talking about math in this class? All right, so what we want to do is I'm just going to give you a visual picture here. So we have a visual picture, and we'll start with a concrete example, okay? So we'll say 471, okay? In other words, I know a particular cell, a particular pixel, is going to have the natural number 471 mapped to it. But I want to reverse this time. I want to know which pixel, what is the x and y coordinate of the pixel that has the natural number of 471. How do I figure that out? Huh? Solve for y. Yep, exactly. So we have to look at the equation, right? We always have to start with the definitions, because the definition is where we get the raw information. So we have to start with that. But one way to do this is the tedious way. You just keep doing like 0, 1, 2, 3, 4, 5. So by the time you get to 471, then you have the answer. But that way may not be very efficient, right? What if I add a few more digits to this thing? Then it would take you a lot longer to solve the problem. So we would like to have a closed form again, okay? So we don't want to use a solution that is unnecessarily lengthy. Okay, so what we're now saying is g of xy equals to 471, and we want to figure out what is the x and what is the y. But we also know what g is expanding to. So we know g of x plus y times x plus y plus 1, the whole thing divided by 2 plus y equals to 471. Right? So now how do you solve for x and y? You got one equation, but you got two variables. Say that one more time? Systems of equation?
Yeah, you have to find like y in terms of x.
Okay, so how does x and y relate? Can you express one with the other? And the answer is no, you actually cannot. Because they are independent. X is not a function of y, and y is not a function of x. Okay, but what I can do is I can define a term m, okay? So I define the term m and say m is just by definition x plus y. Don't ask me why I picked the letter m. It's just, I just picked one, okay? So with this m, I can now say, oh, okay, we can simplify the equation just a little bit, right? So we have m times m plus 1, the whole thing divided by 2 plus, we still cannot get rid of that y, but that's okay. Is that okay? I'm just utilizing the definition of m to make it look nicer. Yep.
M would be the location on the x-axis?
M would be the, yes, it would be the intercept of the diagonal line with the x-axis. Yes. Okay. So there's a certain significance to m, but there's no way I can solve x and y and m at the same time, because m is defined using x and y are independent from each other. So we're not gaining additional information. We're just presenting the equation in a slightly different way. Okay. Okay. So let's work this out a little bit more. And we say, oh, this is just m squared divided by 2 plus m divided by 2 plus y equals to 471, right? I'm just expanding and using distribution. So no heavy duty lifting here. We look at this and go like, we almost have a quadratic equation if it's not for that stinking y. Right? That stinking y is just in the way. Okay. But we'll try to arrange everything so that it looks like a quadratic equation with that stinking y still there. Okay. Is that good? All right. Well, but y actually has some constraints because y cannot be negative. We know y has to be non-negative. It can be 0, but it cannot be negative. All right. So if that is the case, if y cannot be non-negative, cannot be negative, can I do this?
M over 2.
Say it one more time.
L over 2.
Yeah, you've got the.
Oh, so over 2. Okay. There we go. Thank you. But can I go from here to here? Less than or equal to, because y can be 0. Is that okay? So I turn a equality into an inequality, but at the same time, I lost that troublesome y. Is that okay? Can we solve this as if it is a quadratic equation?
Yes.
Sure we can. It has 2 roots, right? Because it's a quadratic equation, m has 2 roots. One root is going to be positive, and the other one, guess what? It's going to be negative. We can toss 1 away because m cannot be negative. So now we have solved for m. After we solve for m, what else can we do? Plug it back in here, solve for that y. Once we have m and y, then we can solve for x. Problem solved.
Okay.
Is that okay? So what if this side is not 471, it is just some n? Well, then you just cross out all the 471 and substitute with n. You still solve the quadratic equation based on that m, based on the n. So what I'm saying here is instead of using a concrete number, okay, I'm going to use a different color green here. Just think of this not as a concrete number, except it is lowercase n, some natural number. So you still end up at this particular point where it becomes a quadratic equation that you can solve. Is that okay? Yep, go ahead.
So I thought I understood why I went from inequality to inequality, but I think I mixed it up. So are you just saying that like the quadratic with m squared over 2 plus m over 2 plus y is a positive number, so if you take the y out and subtract 471, you're subtracting a big, smaller number minus a bigger number, and that's why it's less?
Yep.
Okay.
Yep. So going from this step equal to 0 to the last step, which is less than or equal to 0, relies on the fact that we know y is non-negative. Yep. But because of that, we can basically now get a lower bound on m, and then you can also do an upper bound on m by let me see. The lower bound by itself will solve for m already. So this is basically what we need to do to solve for it. So when you go back to the notes, I got everything typed up nicely. So okay, I use a different letter. Instead of m, I use the letter w. Look at that as m, but it's a vertical mirror image, right? So close enough to me. So we got this, and then we get to here, same format. Get to here, and then we end up with this by, I just multiplied 2 to the entire equation, that's all. But we ended up with this, quadratic equation, and then you can solve for that w. So w, if you just plug it into the quadratic equation solver, you get this particular form. Because we can toss away the negative side of it, so we end up with only this one thing here. It's not going to be a rational number, or for the most part, it's not going to be a rational number. So we just say, let's take the floor function of that, so to turn it into a natural number. Yep.
Why the floor and not the ceiling?
We have to take the floor and not the ceiling, because the ceiling is going to break the less than or equal to requirement in the quadratic form. So we have to take the floor, which is the closest natural number that will still make it. It will be the largest natural number that will still make it less than or equal to 0. So that's why we need to take the floor of that. So that's it. Once we solve for w, we plug the w back into the whole thing, then we can solve for x. We can solve for y first, and then from y and w we can solve for x. So the rest of the math is just going backwards. So with everything said and done, so I define a new function called w of n. Okay, so w of n is just defined like this, which is copy from before. I just parameterized w. Okay, because before w is just a variable. Now I just turn it into a function so that w of n depends on the value of n. That's the only change in here. So with that being parameterized, now we can solve, work out the algebra stuff. So we can now solve for what is the inverse function of g applied to n, which is a natural number. It turns out to be x of n and y of n as defined earlier. But if I expand what is x of n and y of n, this is x of n, this is y of n. So the result of the inverse function is not a single number. It turns out to be a two-tuple because we need a coordinate back. Is that okay? Cool. So once again, I could have just given you this without all the derivation in between. But since I spend the time to do all the derivation, I go like, let's not make it go to waste. We'll put it here in the notes too. Because it kind of explains the line of reasoning. I'm not claiming that this is the quickest way to get to it or the best way to explain it, but it still explains how I derive the inverse function of g, which is kind of me trying to explain how I think. So is that okay? So, all right, so let me go back a little bit and point out, so this stuff here, all of this stuff, and all of that stuff, pine needles, okay? What is the pine tree? Pine tree is basically just saying, oh, there's a function g to go from n Cartesian product with n to n. But because it is bijective, there's also a g inverse to go from n back to n Cartesian product with n. What does g look like? That's part of the tree. So the pine tree says, okay, if you don't really care about the derivation and stuff like that, then we know, well, where is that g? Where did I put it? Right here. Okay. So this, if you look at the whole tree, this is part of the important part of the tree, is g of xy looks like that. But the other part that is also significant and useful is when you look at g inverse, it looks like that. So that means you can give me a coordinate, and I can tell you what natural number maps to that coordinate. But I can also reverse the process. Give me a natural number, and I can tell you what the coordinate is corresponding to that natural number. So are we good so far? Hmm? Unless you have a photographic memory, you probably have a chance to do it. If you have a photographic memory, then you have memorized, everything that I have just presented, so it won't be very original anymore. But if you don't have a photographic memory, that means you just remember the conclusions and the idea along the way, but not quite the actual math. So yes, you can go ahead and give it a try. It's a good exercise, I would say, but don't spend too much time on it. But most of this, really has nothing to do with, higher, math. It really is just algebra. As I said, the biggest trick of this entire derivation, for g inverse, is to turn it from an equality equals to 0 to less than or equal to 0, and therefore losing y. That's the biggest trick. The rest is for the most part just algebra. Is that okay? Are we good? All right, cool. So does it have any practical use? Yep, go ahead.
Well,
quadratic equation so has two solutions.
Yes.
So what are you going to select each one as?
Because we know W cannot be negative, so we automatically get rid of that one. So your argument is kind of explained here because W has two roots. So the polarity of the roots has to do with this plus minus here. So because we already know it's a -1 to begin with, so that means if I choose the minus over here, then the whole thing is going to be negative, which is not what we want. So that's why we toss the negative, the minus away, and only maintain the positive. And that's how we chose, the one root that is going to work. The other root is not going to work. So are we good with the G and the G inverse, functions? But basically it has to do with collapsing a two-dimensional space into a one-dimensional space. And because you can nest, G within G within G within G, now you can collapse any dimension, known, finite dimension using natural numbers into a single dimension of natural numbers. Okay, it's all good? All right. So instead of transmitting, a coordinate using like 2 or 3 numbers, now you can just send a single number as long as the other side know how to apply, G inverse, the other side can reverse it back to 2 numbers. So we're good with this? Does anyone want to know, where 471 is supposed to be at? Yeah. I'm not letting that go. All right, so we'll give it a try. I'm just thinking about using whether I should use a spreadsheet that's on the computer or whether to use a Google spreadsheet. The Google spreadsheet is cool in a way, but it's always kind of slow, which I don't like. So I'm going to use a spreadsheet here, just kind of continuation of what we have before. And then we have a column for n and a column for W of n. So n is 471. So we just have to apply this function here to figure out what is W of n. Okay, so W of n is defined here. I just have to enter that into the spreadsheet. So we got the floor of the square root. Does it have square root? SQRT? Yep, it does have square root of 8 times n plus 1. And then after the square root, we have to subtract 1, and then the whole thing divided by 2, and that ends the floor function. All right, so W of n is 30. Then we need to figure out y. Okay, so y is, let's see. So y is going to be 471 minus our W value times W value plus 1, the whole thing divided by 2. So y is 6. And now we can try to figure out what is x. X is the W value minus the y value, which turns out to be 24. Well, how do we know whether that's right or not? Does anyone want to draw the whole thing out and check whether the coordinate at 24, 6 actually is 471? I have the large whiteboard. Yep, we just apply to G. So we will separately apply G to this whole thing. So G is, okay, first we have x plus y times x plus y plus 1, the whole thing divided by 2, plus y itself. So I'm entering the G function entirely independently, so I cannot basically have a misunderstanding and have 2 mistakes to cancel out each other. Okay, press the enter key, and we got 471. So I have relative confidence that the equation is working out. Is that okay? Question?
Using again to find just
Individually
individually y and
x
x and y.
and y? Okay.
That's coming from
So this is what is given to you, 471. And then by applying the w function, which I just copied from my notes here, I get the w. But w is the sum of x and y. Yeah. But more importantly, if I just use the w and find out what is the value of the base of the diagonal line, and then subtract that away from 471, that is y. So once I get y, and I know the sum between x and y is 30, then I just have to subtract y from w, and that becomes x. So are we good so far? Cool. In previous semesters, many students have tried to look for additional literature on this particular function or this particular mapping. As it turns out, there are many books that refer to this particular way of mapping a two-dimensional natural number space to a single natural number space, but nobody bothered to use closed form equations to express G or G inverse. I'm too lazy to actually read books and do research, so I just decided I'll just do it myself. It would take me less time. So are we okay so far with all this stuff? Cool. So we are done with function stuff now. Okay, so if you're in the class notes, we are basically done with all of null, which means I can give you a new homework assignment. So this is the homework assignment for functions. It is open now. You have until you have 1 week to work on it. Basically, it's going to be due at noontime next Wednesday. So you got a week to work on it. I would suggest that you start early, so that if you do encounter some problems or questions or need clarifications, you can come to my office hour. You can ask those questions in class on Monday. So you got a few chances to kind of address any issues with concepts of functions. Yes. One attempt. But once you open it, as long as you do not submit it, you can continue to work on it and change answers of something that you answered already. So just leave it open until when you need to turn it in. So that reminds me to go back to the set theory homework assignment, okay? Because I want to see if you guys have any questions. So I'm going to go through the whole thing myself. It's due today, so we can't really work on it anymore. But I do want to kind of go through this myself and see if I can answer any questions that you might have. So okay, question number 1. Uppercase A is AB, lowercase b, uppercase B is A, B, and C. So which of the following is true? And only one, okay? Because it's a round bubble, you can only pick one because it's a radial button. So in this case, A is a subset of B, is the only one that works, okay? The other 3 simply are not true, okay? So we click the first one. And then question number 2 is something I have to grade manually. So it is giving you a constraint, okay? So the constraint says, uppercase A union with uppercase B has to come up with these 5 elements, okay? That's part of the constraint. The second constraint is if I look at everything in A but not in B, it will only be C and E. That's the second constraint. So I want you to tell me how I can arrange element membership between the set A and the set B so that this constraint is satisfied. That's basically what the question is asking. So basically, you need to list what is in A and what is in B. Okay, so let's go ahead and start with A. What do we know for sure is in A? C and E, right? Because those things are in A but not in B. Based on this is what is in A, what is going to be in B? Exactly. So you have A, B, and D. That will work. Yeah, sure. Yeah, you can have additional stuff in A, but A must have C and E, and B cannot have C and E. So that's the restriction. So there are multiple correct answers, but this is the simplest. Yep.
So for A, I put A, B, C, D, and E. That'd be fine.
A can have A, B, C, D, E, correct.
Yeah.
The whole thing. Yep. That works too. So the key is, A must have C and E, and B cannot have C and E. But together they have to cover A to E. And that's the restriction. So are we good with this one? All right. So let's move on and talk about number 3. Choose the correct answer. You got a 50-50 chance to get it right, even if you know nothing about this sort of thing, right? So the question is lowercase a an element of a set that has one element which is by itself a set that has A as its element? And the answer is false. Membership that is not recursive. There's no -r. So it is false, okay? This is a very important concept, okay? If you got it wrong, the point deduction is very negligible, in the grand scheme of things, but it is good to understand that, it does not nest. When I ask, is something an element of something else, it is not going to be hierarchy, it's not nested, okay? Because the set that contains the element of A is not the element of A. And that itself basically make this answer no, false. Yep.
So it's like the element has to be in the outermost layer of the
Right. It's a single layer consideration. It's not nested. Okay, question number 4. Choose the correct answer. Is it true or is it false that ABC is a subset of itself?
Yes.
Yes,
But it's not a true subset.
it is true. Okay. Okay, question number 5. The union of ABC and AB is ABC. That once again is true. The equality holds. Question number 6. So it's, okay, this one is kind of, you have to read it in a particular way because it says regardless of the definition of A and B. In other words, no matter what I give you as set A and what I give you as set B, does the following hold true? So just being able to work out one example where, I can make it true, doesn't work, okay? You have to say, give me any set A, give me any set B, that is still true, okay? So if you want to prove it is not holding, if the implication is not holding, you have to give me a counter example, okay? Find me a case such that this implication is false. If you can find one single instance of this is A and this is B, and that implication is false, then you can answer false for sure. Okay? So how would you approach this case? So A minus B equals to an empty set means, A is a subset of B, because, that's one way to define, subset of. So if it's a subset of, it has to be everything in A is in B. Okay, so we know everything in A is in B. But does that imply that A is not a proper subset of B? No. Because A and B can be the same. So if A and B are exactly the same, then A is a subset of B is going to be, proper subset of B is going to be false. But not false is true, so that is still okay. So in order for this implication itself to be false, you have to find me a case where A is a subset of B, but this negated expression is false. But for the negated expression to be false, that means A is not a proper subset of B. Can you find me a case like that? When A, yeah, go ahead.
So A should be empty set.
A doesn't have to be empty.
It can be empty set.
A can be empty.
And B have to have empty set as an element too. So empty set is always the subset of every set,
That is correct.
and B has the empty set as an element too. So is that right? So it's gonna be true.
Okay, so let me see if I can work this out in steps. And where is my... I have that problem again. Okay, but I can use this to work it out. Okay. So the question is asking about A minus B. Oh, okay, I'm still using the wrong color. Equals to an empty set implies the negation of A is a proper subset of B. Okay, but first of all, we have to understand implication. So with implication, okay, X implies Y, and here's X and Y, 0, 0, 1, 1, 0, 1, 0, 1. So for the implication, this is true, this is true, this is the only case when it's false, and this is true again. Okay, so what we are looking for is, if we want to say it is false, then we are looking for a case where this part is true, but this part is false. But in order for this entire part to be false, it also means that A is a proper subset of B, has to be true. So I just need to find a case where A is a subset of B, but A is also a proper subset of B. That's an easy one to find, right? Yep.
If A is a proper subset of B, then A subset of B is always true. No?
That is correct.
So
But I want the implication to be false.
yes, so if you can make proper subset A be true, making the implication false, you still make the subset of A and B always true.
So we can make it happen.
So we can make that.
Yes. So a very simple example is when A is an empty set and B is non-empty. Okay, it doesn't matter what it contains. This will make the implication false. Is that okay? Well, if I can find one single case to make the implication false, that means it doesn't universally apply, which means the answer to this question is going to be false. Is that okay? All right. How about the next one? Doesn't matter how I define A or B. If I say A is the intersection between A and B is the same as the union between A and B, does that imply A and B are the same? Yes. The answer is yes. All right. And then question number 8 is the best one. So this one, once again, is to say, okay, give me any A, give me any B. Is this implication always true? So we work it out the same way as before. Okay, can we find a case such that A is an element of B and A is also a subset of B? Because if I can find something like that, then I can answer false for sure. Okay, can we find something like that? Pretty easy, right? So the answer is false here, and I'm going to go back to the other slide to give you an example. Oops, not this. There. Okay, so this will actually, no, this is not going to work. So I can make A equal to, let's say, just lowercase a. I can make B having lowercase a, but also the set that only has A in it. That will make both conditions true. Because in this case, is uppercase A an element of uppercase B? Yep, it's right here. But at the same time, is uppercase A subset of uppercase B? The answer is still true because they both have the element A. Since I can make this happen, then the implication can be false, which means it is not true for every single case of A and B. Is that okay? All right. So that's all the answers to that particular homework. And now we can move on to a new topic. Are there any questions about this particular quiz or homework assignment? No questions? All right. Yep.
I want to clarify about the recursive and what you meant by that is the second half of that equation. What exactly that means? We have a set that contains a set with one element,
Mm-hmm.
and that doesn't equal the element.
Correct. Okay, so let me use this screen to try to explain that. Okay, so can we agree that the element A or the value A is not really the same thing as the set containing that value? Is that okay? Okay, so we can now establish that this is true. So now when we say is A an element of a set that has a set as an element that has A in it, can we say that this is false? Does it follow that this is false? Is that okay? So that's what I meant when I say, membership, or containment is not recursive when we look at the element of operator. So the element of operator is not asking, does anything within this set at some level contain the value A? It is at the top level only. All right, so I think we are ready to move on to talk about relations. In a way, it is a fun topic. And the example that I use is certainly kind of interesting, one of them. All right, so we want to explain what is a relation. So a relation is basically a subset of the Cartesian product of a set with itself. So it's not a function, okay? So the first thing you need to remember is even though it has something that seems like it's a function, it is not a function. Because a relation relates elements of the same set to something of the same set, okay? So it's not like you have a domain and a codomain. Nope, you only got one set, but you're defining how elements of the same set relate to each other or itself. So an element can relate to itself, okay? So the first thing we notice is a relation R is a subset, not necessarily a proper subset. It can equal to, but it is a subset of X Cartesian product with X. So this is how we say R is defined over a set X. That's just terminology. That looks pretty abstract, bunch of symbols, right? You can look at R as parent of, as a relation. And X is the current population. Okay? So you pick an element out of the current population, okay, Tommy, and you pick another element of the same population, Jack, okay? Then you can ask whether there's a relation between those two. Is Tommy a parent of Jack? It can be true. It can also be false. Is that okay? So that's what a relation is, yeah, go ahead.
What would you call it if it were like a set of tuples that wasn't a function, but also wasn't the Cartesian product of the same set? Would you just call it like a mapping or something?
So it would still be a subset of a Cartesian product of some kind.
Yeah.
You can call it a mapping, but it would still fit into a relation meaning, because a relation has no other constraints. It only has to be a subset of the Cartesian product of a set with itself.
What I'm asking though is, what if instead of R is a subset of X cross X, it
Uh-huh.
was like R is a subset of Z cross N or something?
It cannot be. It has to be the same set.
Yeah. What I'm asking is, if you couldn't call that a relation, and if the tuples play out right, you could also not call it a function. So then what's like?
I do not know of a general term to describe that.
Okay.
But is this part okay? All right. So from the perspective of notation, we can say, if I pick an element x and I pick an element of y from x, uppercase x, if they do relate, then we say that x or y is true. If they're not related, then x or y is false. Okay. Are we doing okay so far? Okay. I can give you one super concrete example. Okay, so the super concrete example in section 3 uses the operator or the relation less than, and we want to define it over the set of all integers. Okay, so, well, do we have a problem with 1 is being less than 2? Okay, 1 is less than 2, so that means 1, 2 as a 2 tuple is in the relation less than. So we look at the relation as a set of 2 tuples, and as a result, 1, 2 as a 2 tuple is an element of less than as a relation. And the relation is defined over integers, so that means the relation itself is a subset of integers Cartesian product with integers. Is that okay? Yep, go ahead. Question?
That makes sense. When we're talking about the Cartesian product, you're basically trying to figure out if two elements in that same set, if their cross product is equal to the product that they produce, right? Like two different elements, when you multiply them together, should equal this, right? Is that what you're looking for in a relation?
Not exactly. I don't think so. Okay, so let's take a look at this, less than thing. Okay, and I can give you more or less a better idea of what is in. Okay, so we want to define less than over the set of all integers. Okay, so in other words, I want less than to be a subset of z Cartesian product with z. Okay, to basically indicate which member of integers is less than which member of integers. That's all. Okay, so if I really want to spell this out, it's going to look really boring, right? Because 1, 2 is in here, 23, 60 is in here, -3, -2 is in here, and so on. I mean, there's an infinite number of elements in this particular relation, but that's the general idea. Okay, is that okay? Do we have a problem with 23, 60 as a 2 tuple in being inside the Cartesian product of z and z? Nope, that's where it belongs. Okay, what about 0, 0? Well, 0, 0 does not belong in this set because 0 is not less than 0, so it's excluded from this particular set. So that's the idea of a relation in discrete math. So do we have any questions about relations? Just a general idea. Okay, no questions? All right, so if there are no questions about relations, and here's a random one, okay, totally random, no particular reason. So I just decide, okay, let's look at the X, a set with A, B, C, D as elements, okay? Don't ask me why, that's just what I use as an example. And I define R as a relation to be exactly that, okay? A relates to itself, A relates to B, B relates to C, D relates to D, B relates to A. Don't ask me why, because that's just an example. It's completely arbitrary, okay? But now the question is, what about the notations? A or B is actually true, because through the relation R, A relates to B. It's a notation thing. What about is the 2 tuple BC in R? Well, BC is clearly in the set R, okay, so that's true too. So you can look at this as a 2 tuple being in the set, but you can also look at it as B relates to R. B relates to C. So it's just two ways of looking at exactly the same thing, different ways of spelling it out. Okay. How about B relating to B? Nope, BB is not in the set. What about DC as a 2 tuple? Is that in R? Nope. So once again, you can use set membership to express that, but you can also say, does it relate through R to express that? That's what this example is trying to illustrate. Okay. Yep.
So it depends by what operation you are selecting as relation.
And in this case, it's completely arbitrary. There's no particular meaning to this R, other than just to serve as an example. So just like functions, the functions that we define only has to meet certain requirements. But what value maps to which other value can be completely arbitrary. So it's the same thing. Exactly. There no particular. There doesn't need to be a structure to it. Okay. But now we're going to look at some properties of relation. So we will get back to the quantifiers and stuff like that now. The first one is whether a relation is reflexive. Okay. So a relation R over a set X is known to be reflexive if and only if the following is true. Give me any element, E, okay, and E has to be in R. In other words, E has to relate to itself. If this is true, if you can show me for every single element in the set X, it relates to itself, then the relation R is known to be reflexive. Is that okay? All right, so let's go through some examples. All right, and so let's say X is AB, oops, AB, and R is AA, BB, oops, and AB. There we go. So is this R reflexive? If I look at A, does it relate to itself?
Yes.
If I look at B, does it relate to itself?
Yes.
It is reflexive.
Yep.
But tag, there's something else in the set. I don't care. AB here does not matter at all, because all I need is everything to relate to itself. We can have additional relations in the set. No problem. Okay? So being reflexive is basically just defining the minimum, okay? What it takes minimum to be reflexive. But you can have additional stuff in it. That's fine. All right? So that is kind of important. What about this one here? That is not reflexive. I mean, sure, A does relate to itself, but B does not relate to itself. It is not reflexive. So the first R is reflexive, the second R is not reflexive. Okay?
Hmm? It's the first two tuple is AA, correct?
Yep. Oh, that's bad penmanship there. That's A.
Okay.
All right, so that's reflexive, and here's symmetric. Symmetric is a little bit awkward. Okay, symmetric says it's not the worst either, but it's just a little awkward. So a relation R over a set X is known to be symmetric if and only if the following is true. Pick me any two elements in X. Can they be the same? Yes. Do they have to be different? No. Can they be different? Yes. Okay, so pick me any two. The following has to be true. If you find EF as a two tuple in R, then FE has to be in R too. What if EF is not in R? Well, then you better not find FE in R. Okay, because this symbol is if and only if, which means in order for the if and only if to be true, if one side is false, the other side has to be false. If one side is true, the other side has to be true. So that's how we define whether a particular relation is reflexive or not. So let me ask you this question then. This is X, and this is R. Is it symmetric? It is symmetric. So choose any two elements as my E and F. Okay? E is A, F is B. Okay? Is it in the set? No. What about the other way around? Also not in the set. False, if and only if false, is true. What if I give you this? So this is symmetric and obviously not reflexive. What if I give you this? I just got AB in it. Is that symmetric? It is not symmetric because I find AB in the set R, but BA is not there. If I find one, the other one has to be there too. If one is missing, the other one has to be missing. So in this case, one is there, the other, the mirror image is not there.
So if you eliminate the parentheses around AB in R, then it's symmetric, right? You're looking at a tuple instead of two different elements.
It has to be a two-tuple. So every element in a relation has to be a two-tuple. Yes?
You had a relation with just one element that was A, would that be symmetric?
Well, let's try to answer that question. It's not symmetric. So now we look at R only having A in it. Okay. Is it symmetric? It is symmetric because when you choose E to be A and F to be A, then AA is true on one side, but AA is also true on the other side. So it is still symmetric. Yep.
So that means all reflexive sets are also symmetric.
No.
Why not? If you had for something to be reflexive.
Reflexive only says that AABB have to be in the R, but you can also just have one AB but not BA in the set. That makes it not symmetric. Is that okay?
Yeah, I think so.
If a relation is just barely reflexive, then it is also symmetric. But if I just tell you it is reflexive, it can have some additional stuff to make it not symmetric.
So this is saying every element in the set needs to be, for this to be symmetric, every element in the set needs to be symmetric. Like you need to have A, B, D, and those are the only.
I would go back to this definition.
Okay.
Yep. Consider every way to pair up the values of the set. If you can find one in R, you better find it the reverse in R as well. If one is missing, the other one has to be missing too. Okay? Is that good? Okay. So now we move on to transitive. So transitive is actually not too difficult to understand because we already understand, a lot of relations that are transitive, like less than or equal to, those are all transitive. So this basically says choose any three things out of the set, okay? So for every single way to choose three things out of the entire set, they can be the same, they can be different, two can be the same, the other one is different, I don't care, okay? So pick me three things out of the set, E, F, and G. If EF is in R and FG is in R, you better find me EG to be in R. So if this implication is true for every way to find three elements E, F, and G in R, in X, then that relation is also known as transitive. Is that okay? So let's do some exercise. So obviously, first of all, if this is X, A, B, and this is R, is it transitive? Yes, it is transitive. Why is this transitive? R is empty. Well, let's go back to the definition. So when we go back to the definition of transitive, since it's an empty set, do you think this membership is going to be true? No. So that makes this conjunction false, right? I don't even need to bother with the second one. That makes the entire left-hand side of the implication false. what does that make the implication itself? True. Oh, okay. So that is why an empty set is transitive. Is that okay? So implication is very tricky because if you can make the left-hand side false, then the implication is automatically true. So the only way to make an implication false is for the left-hand side to be true, but the right-hand side to be false. Okay? But if the left-hand side is guaranteed to be false, I don't have anything to worry about. It's true. Is that okay? So that's one thing that you kind of have to keep in mind pretty much for the entire semester, because there are a lot of concepts based on that understanding of implications. All right, so we're moving on to anti-symmetric, which is not the same thing as not symmetric. Okay, anti-symmetric is not symmetric. Okay, so let's look at the anti-symmetric definition, which is kind of odd. We start off with kind of the same kind of quantifier. Give me any two things in X. Okay, they can be the same, they can be different, but give me every single possible way of finding two things in X, E and F. So the implicate is once again an implication. The implication says if EF is in R and FE is also in R, then E and F better be exactly the same thing. All right? So let's check out a few examples and see if they are anti-symmetric. Okay? Let's see. Go to page, make a new page. So we'll say X is once again AB. And once again, we look at the empty set first. Is that anti-symmetric? It is anti-symmetric for the same reason that transitive, an empty relation is also transitive. Okay, so we can say, all right, this is in fact anti-symmetric. Okay, what if it has AB in it? Is it anti-symmetric? It is anti-symmetric because AB is in it. Where's BA? Not in it. But in order for the left-hand side of the implication to be true, AB and BA, they both have to be in the relation to make the conjunction true. I cannot even make the conjunction true, which means the left-hand side of the implication is false, which also means the implication itself is true. Woohoo! So this one is, in fact, anti-symmetric. Let's look at this one, AA. And BB, is that anti-symmetric? Yep, it is anti-symmetric because AA is in here, AA is in here. That makes the conjunction true. But does that imply A equals to A? Yep, it's the same thing. And the same thing applies to B. All right, so this is also anti-symmetric. Okay, can we make something not anti-symmetric? I'm sick and tired of everything being anti-symmetric. Absolutely. That is not anti-symmetric. AB is in it, BA is in it, right? So that makes the conjunction true. But A and B are not the same. So that makes the right-hand side of the implication false, while the left-hand side is true. Well, that means it's not anti-symmetric. So this one is not.
Assuming A and B are different.
Correct. So A and B are assumed different. Yep. So are we good so far? Yep. Mm-hmm. Oh, okay. Let's see, we're out of time. So one comparison operator that you already know is anti-symmetric. Less than or equal to is anti-symmetric. If you find me two variables, if x is less than or equal to y and y is less than or equal to x, then x and y must be the same. So less than or equal to is one relation that is anti-symmetric, but it's also transitive. Yep.
Which logical condition you are going to check both for multiple sides inside the expression?
I am not.
It's NAND, not AND, not OR, XNOR. Which one is the expression you are using?
Well, it's the ordering. So I use parentheses to indicate which one to go first.
Yeah.
So in this case, we check the membership. We check the membership, and then this is either true or false. This is either true or false. Then we take the conjunction, right? So this is the whole thing is either true or false. This is either true or false. So now the question is, does this imply that? So the parentheses indicate the order of the operators. Question? Mm-hmm. Oh, no worries.
I thought I understood. You said you three of the automatic points. So I'm planning to come to the office hours on Friday, but do you know if there's like a beacon tutoring for this subject?
Beacon tutoring I do not know of, but you can go to the Mesa Center or the STEM Center and look for Kevin Kirby. Yeah, Kevin Kirby had taken this class before, and since he's tutoring in the STEM Center, so he can tutor for this class too. Mm-hmm.
They are. There's 14 times -1/2.
Yeah.
Oh, you mean the starting points are scalable?
The test still.
Yeah, if you
Huh?
subtract the starting points.
Yep.
So this is if you subtract the
no
two starting
phones.
points.
Hmm?
No phones.
This
no
is if you
electronic
take the cross
devices.
product.
No electronic devices. That's correct. So if you have some notes that's in electronic form right now, you have to put it on paper.